Hello, everyone. Good morning, good afternoon, good evening to those who are attending this online conference session. My name is Sandeep Kulkarni. I'm working for SABIC now for almost 12 years with major expertise in the application development for the lightweighting, cost reductions, and the design simplicity with the new thermoplastic material. And today I will talk about the coupled simulation approach for the long last fiber material composites in this forum, and hope you will find this interesting and informative. But before going to the actual presentation, I'll give you a quick glance about the company where I come from, SABIC. SABIC is one of the world's most diversified chemical business unit, headquarters in KSA, Saudi Arabia, and it is spread across the globe. As you could see here, we have the four main verticals with the businesses: the petrochemical, specialty, agri-nutrients, and the metals. Would say, the major part of it is coming from the petrochemicals and the specialty. I belongs to the specialty division of it, which is mainly working on developing the specialty resins portfolios for the advanced demanding applications across the segments in the consumer electronics, mass transportations, and the healthcare divisions. Now moving to the main topic, which I would like to cover today. This is the content, which I would cover short intro to the our LNP VERTON profile, which is the long last fibers material, which is the focus area of today's presentation of me. We will also show influence of the fiber length on the properties of the material specific to polyamide based material, why the anisotropic modeling all is needed for that, and how the coupled simulation is helping to solve some of the critical challenges in the industries to help convince the customer on the use of LGF materials. We will also show some of the validation studies, which is important to get the confidence of the customers, and then we will end with the conclusion. Intro about the long last fiber LNP VERTON portfolio. It is mainly based on the long last fiber material produced by the pultrusion process, which help to wet out all the fibers, which is typical mainly here the glass fibers, which is on focus here for us, wetting out all the fibers with the resins as mainly shown in the image over here. Typically the fiber length, the pellet size, we could say is around 11 millimeters in that. And so also we would want to maintain that the longer fibers within our part to help improve the mechanical properties such as higher strength and the higher impact performance. As also you could see, we have put there the portfolio also covered the different resin systems, polyamide based, PP, PBT, PPA, some high heat materials there, which are mainly used to cater to the different applications to meet the specifications for the different industries in that. In today's topic, more detailed, we will go in the technological aspects with the polyamide 6,6 based long last fiber material in the subsequent topics on that. With the long glass fiber material, we also have seen a lot in the literature. There are a significant advantage of it over the traditional short glass fiber material. Here we could see is one very good examples of the seat belt pretensioner. The part has been molded with the VERTON long glass fiber material, while on the left hand side here you could see the image where all the resin has been etched out from the part. So what you see predominantly is just the fibers over here. And this gives a good indication or illustration is how really the long fibers help to maintain the shape and the stability of the part, which is also one of the very important factors in designing of the part. Also having this longer entangled fibers help to give some of the better mechanical properties such as higher impact and the higher stiffness and the strength properties on there. Here we could see some of the other additional properties also enhancement with long glass fibers, which which is possible mainly also with the long-term performance like a creep or the fatigue, where we say the LGF gives a lot more advantages, and also the temperature resistance. So looking into that is having a good mechanical properties of the long last fiber material that makes it a good candidate for the metal replacement applications, mainly for the lightweighting, which is one of the key drivers across the industries. Now, this is the graph where you will see the influence of the fiber length on the properties. And then here we are looking into the three main properties, which is important in the part design: stiffness, strength, and the impact. Now, this graph you would have seen into many literatures or the papers, conferences, which is predominantly is the polypropylene based LGF, where a lot of such similar graphs has been shown. Here in this study, we also make an attempt to make such graph for the polyamide based systems in that. Now, the trend, what you would see here is very similar to the polypropylene over there. Longer fibers gives the maximum advantage to us in the impact performance, which is also logical because longer fibers will help to have a better randomized fiber within the part that gives also the entanglement effect. So that's really help to resist the impact resistance of the structures. The next best we see the strength, and both the impact strength are directly proportional to amount of length of the fibers and the overlap of the fibers with the overmolding resins in there. So there we clearly see the advantage of the longer fibers in giving the better property there. The least affected is the stiffness, which also is very common what we have seen for the other LGF based material also. But that's looking at the two main advantage of the LGF: strength and the impact, in addition to the long-term properties like a creep and the fatigue, makes it fit for some of the applications critical where the short glass fiber may not fit well in that. But having also such good mechanical property, there is still the challenge in the market to accept such material systems into a wider part designs. And one of that reason is the complexity of such material is how it's behave in the real part. Now here you see the one examples over here, which is well illustrate that phenomena. Here we see this is the front end module structures molded with the long glass fiber material. And then we have cut out the specimens at the different locations along this front end module and do the tensile test on this part. Now what you could see here on the graph in this as the variation of the material property along the different specimens in the part. So each specimen also will have the different fiber orientation. So that's really impact the material properties in the part. So you could see a large variations in the material properties within the part itself. Also very interestingly, what we see typically what use the data sheet values, which is normally the molded tensile bars with the fibers will be very aligned in that. You see the data sheet value is much above over predicting the performance as compared to what is there in the reality in the part. So this is one of the challenge with in general with the filled material systems, or also will get more with also the long glass fiber material, that you have the lot more variations in the part with the properties of that as against the some of the metallic structures like steel, aluminum, or magnesium, which is more isotropic. So the property variation is not there in that, right? So there is the industry is more looking into is how to design the part where you have such a variations in the systems. And that's where the advanced modeling techniques and also advanced characterization methods makes it very, very important to bring the confidence to the customers to convert the metal into such thermoplastic material applications in that. Now, one of the way for achieve this with incorporating such process-based material properties into the design of the part is the coupled simulations, and that's what we have targeted in these studies over here. So, what essentially we do in the coupled simulations over here is the anisotropic modeling approach to establish the relations between the processing, dependent on the morphology and the mechanical properties. So what essentially we say here is start with a filling of the part, which is coming from the injection molding, which will affect your fiber orientation in the part. And the influence of that fiber orientation is converted into the local properties within the part, local material properties, and those material properties are used subsequently for the structural analysis of the part. Now, the injection molding is widely used in the industries is the Moldflow software, which is used predominantly by almost all the players in that. So in this study also we have used the Moldflow for the studies. For the microstructural material evaluation, we have used the Digimat software in that, and then subsequently for the structural analysis we have used Abacus. It's there also possibility to use LS Dyna or other structural software also to do the structural simulations on that. But as you could see over here, the process really is using the different softwares for the entire simulation chain to complete. Hence, in order to get the overall confidence on the coupled simulation, it is important to look also each element of it, like a Moldflow, Digimat, and the Abacus, how really they work individually on the aspect on capturing the right behavior of the material. And that's what really we try to capture also individual effect into this study. Now, it's all we have started with the right material characterizations. Now, as shown earlier to you, that typically most of the data sheet values consist of the property based on the direct molded tensile bars as over here, and which all of us know is kind of over predicting the performance. The approach we use in these studies is rather than molding direct tensile bar, molding a shear plaque over here, in which then you have already have some randomization of the fibers within your part in that, which is more than representing the reality with the real part designs in the reality. And then from that part we cut the specimens in the different orientations, 0, 45 and the 90 orientation, and by that also we able to capture what is the change in the material property as a function of the fiber orientation change in the different locations in the parts. And that's what also you see over here in the graph. The orange color line is the property stress strain data at the 0 orientation, which also shows even for the shear plaque, you have the majority of the fibers are in the flow directions. While the other two properties, 45 and the 90s, as you could see over here, is kind of low fiber orientation in that, and that's why you see the lower properties being there. The direct molded tensile bar, as we expected, is showing us a very high properties over there. Now, as also mentioned, the approach typically is taken by the designers to use the datasheet values for the part design. And with that, one could expect that there will be over predictions of the material property than what is there in the reality. So in order to avoid that, many times designer use some thumb rule, like 0.6 to 0.7% of the datasheet value to do the part design calculations. In this approach in SABIC, we always try to do the EATC method, the European Alliance of Thermoplastic Composite method, which is essentially you are doing the lamination theory over here to come up with the material property, which is more kind of a quasi-isotopic property, illustrating a more random fibers within the part. And that's what you see the graph over here, which is falling somewhere between your 0, 90 and the 45 lines. And for the part design, initial preliminary starting part design, sometimes this becomes as one good starting point to design your part. And then you go subsequently to a more advanced anisotropic designs with that. But this data very clearly illustrated how much variation one could expect in the simple shear plaque like this. And it will get more and more complex when you have the very complex applications. The next step of this then is, can we able to predict then the right fiber orientation within the part? And that's where we have performed these simulations in the Moldflow 2019 version. Also in this study, we have worked very closely with one of the Moldflow engineers on that. So whole process, this started with getting the samples from the center locations of these tensile bars and perform the CT scan on that part so that we get the real fiber orientation at the function of the thickness of the part, as shown dots over here, lines. So that is the experimental data which we have received. And then for the simulation, we have used the ARD RSC model, the model which is been also recommended by Moldflow for the long loss fiber materials systems. Now, when we started with the ARD RSC model with the default setting, as you could see here with the dotted line, what we have observed that it is showing a more random fibers also in the skin, which is a bit different compared to what we have seen in the experimental results in that. So that's where we have done some optimization of these parameters. The ARD RSC parameters mainly consist on the kappa factor and the phi, the B1 to B5 factors. So those factors we have optimized in that, and that helps us to push the skin prediction a bit upward, and that is more close to representing to what we see in the reality in the experimental results. But still what we would see that it is could not exactly able to capture the skin core relationship, the transition happening between the skin and core, and also more importantly the core depth it could not able to capture well with that. So the other additional approach we have taken in this study is try to increase the number of mesh element through the thickness of the parts. So we have gone up to also the 30 layers per thickness. With that, what we could see is we could able to capture the core depth to a certain accuracy. As you see, the at z is equal to 0, we could capture it quite well. But still there it is cannot able to capture mainly the core width part of it and the transition part of it. Now, some of these factors also during discussion with the Moldflow engineer, they have mentioned that this is something, the effort which is currently ongoing at Moldflow of improving it, and which is essentially how to incorporate the viscosity variation as the function of the fiber in the part, which is also varies more when you have the higher fiber loading. So that is one of the aspects need to be incorporated into that. But the skin aspect, what we have seen is capturing well with the Moldflow simulations. Now, having got some understanding with the Moldflow and how it capture the behavior, the real fiber orientations in the part, the next part of it is how to capture that into the anisotropic modeling. And that's what the next step of it is the Digimat, which is used mainly to capture the locally different microstructures information from the Moldflow, which is essentially the fiber orientation in the part, and then convert them into the local material properties, which can be used subsequently for the structural analysis with Abacus, LS-DYNA, Nastran, or any other such equivalent softwares. Now, in the Digimat, it all starts with giving basic informations of the matrix properties and also your fiber type and the fiber properties with also L over D ratios for the fibers. Then it use its own homogenization process approach to the homogenization of the material properties, and then subsequently develop the anisotropic material model, which could able to capture the behavior of the material as a function of the fiber orientations in the part. So at the end of this exercise, what essentially you will have the anisotropic material card available. Now here you see the three examples where we have developed such material card and then done validation with the experimental results for that. Now the first one is with the quasi-static conditions with the different orientation 0, 45 and the 90, where we incorporate the elastoplastic models in that. And here what you could see the comparison of the experiment versus the Digimat. And for all the three locations, we could see we could capture the experimental behavior with reasonably good accuracy with that. Right. The next is then is using it for also the high strain rate effect. So how the material behave and how we can capture that effect with the high strain rate, where you could also expect with the higher strain rate, your material becomes more stiffer with that, right? Now here they have the different models available with Digimat, the Elasco viscoplastic model or the Visco Elasto viscoplastic models, and then it's depend upon which is the best suited model for you, looking into the behavior of your material, because each of these advancement or the advanced model will also lead to a higher computational time. So you have to be the designer, have to be put a well thought of which is the right model for him. Now here we have seen the comparison for the different strain rate values. The one is for the 0 oriented tensile bars and the one is for the 90 oriented tensile bar. Now by far for all these results, one could see that 90 oriented stress strain data is always on the softer side as compared to the 0 oriented tensile bars. And also as the function of strain rate, we could also see there is a stiffening of the material response as a function of strain rate, which is also very typical observed behavior with such material systems. Here also we could see the comparison of the Digimat versus Moldflow largely across the different orientations and across the strain rate. The Digimat able to capture the behavior quite well with the experimental results. Would say this is more or less within the 5% accuracy we would see the behavior has been captured in that. The third one example over here, which is more for the long-term behavior, because first two what we have seen more kind of short-term behavior with quasi-static and impact. The long-term more with the creep behavior, where we have tried to see how the anisotropic model could able to capture the reality with the experimental results over there. Now here there are again the various models available with the elastoviscoplastic, where also you could add the temperature effect into these models and then work with the Prony series in that. Now we could see here for the major part of elasticity and also a part of plasticity regime, we could say the Digimat able to capture the experimental behavior with rather good accuracy. We see only the one of the limitation where with very high plasticity expected in the material, in that case there is a certain gap between the Digimat and the experimental results. So but most of the other part of it we could say it is capturing very well behavior. Now this gives a confidence on how really the anisotropic material models behaves and how it captures the Moldflow data, the fiber orientations, and then use to convert it into local properties to capture the behavior of the part. Now, with that initial confidence on the individual software behavior in capturing the real response, next we move to the validation of such models into the real part. And for that purpose, we have taken this long beam, the beam which is available at SABIC. This is the 1 meter long beam. So kind of a long beam, which was also, we have designed so that it is more represent some of the real applications in the automotive or but also in the other industries on that. Now this beam also have the 4 gated systems with also possibility to do the different filling sequence with this part. So we have tried the 3 filling sequence with such part, the all gate open sequence. So in that the gate 2, 3 and 4 open at the same time. The second one is the inside out, where you are start filling from the gate 3 and then go subsequently opening the gate 2 and 4 when the flow front reach at that gate. And the third option where we have done the top to bottom approach, where we start with the gate 1 and subsequently open the gate 2, gate 3 and gate 4 when the flow front reach each individual gate on that part. Now with each of this filling sequence, one can imagine there will be the variations in the fiber orientation as the function of how the flow is being defined in the part. So that will give us some interesting results, is how really the combinations of the Moldflow, Digimat and the structural software, which here we use the Abacus, how it able to capture this behavior well with the experimental results. So we perform also the experimental studies on that for the static impact and the creep loading conditions, and that's where we had done the comparison with the numerical studies. At the current stage, we are also performing ongoing some studies where we are doing these studies also for the fatigue behavior and try to capture it with the anisotropic studies on that. But in today's presentation, I will more try to cover static impact and the creep behavior of it. But again, we have started with the basic. We first try to see how, again, for the real part here, how Moldflow able to capture the behavior, the fiber orientations, again, which is the main base, would say, for the anisotropic simulations. So we have here for the beam part, we have cut the specimen at the two locations over here as shown, the number 1 and the number 2, and then have the CT scan data from that, the experimental results, and then do the mold flow simulation over here for to see how the comparison looks like. Now here we have directly used the optimized parameter, which I have shown you in my previous slide with the shear plaque. So those optimized parameter we have used here directly for the studies. Now here again, same, very similar to the shear plaque. The observation is similar. What both the position 1 and 2, we could see that on the skin it could capture the behavior observed in the experimental results with rather good accuracy. Would say with 5 to 10% variations, but it could capture it quite well. Similar to shear flow or shear plaque, also what we have seen in the core region mainly, where in the experiment we have seen some deep in the core, which is indicating more fibers are orthogonal to it. With Moldflow, we see it could not able to capture that effect. It is rather showing all aligned properties in that. But in this one, even we see some of these variations are there within a small gap of the total thickness of the part. But the skin effect, it is capturing quite well with that. So with that, we move to the first validations with that study, the quasi-static test on that. So as you see here, the setup at our facility, the beam, as you could see over here, which is then subjected to the 4-point bending load test on that. And then we capture the force and deformation from that test study. Now this testing we perform for 3 filling sequence, as I have shown you earlier, all get open inside out and the top to bottom. And here you could see the dotted lines. Now, as also we have mentioned, as a function of the filling sequence, you should expect the variations in your stiffness, and which is also very well is shown over here. One could expect with the top to bottom approach, where your fibers are, you are really aligning in the direction of the beam. So in the bending direction, we have seen the maximum stiffness for that particular beam, and subsequently lower for the inside out approach, and the least one for the all get open, where in the all get open one could expect a relatively randomized fiber orientation. So the trend which observed in the experiment to what we could expect is following actually quite well. And here you see the solid lines, which is the anisotropic results, where the fiber orientations from the mold flow are being transferred to the digimat, which will capture the individual material property for each of those locations where the fiber orientation has been taken out, and then do the subsequent analysis in the abacus. Now here we see for all the 3 results, importantly, it could able to capture the variations in as a function of the processing quite well, which also indicating this variation is captured well by the Moldflow softwares, and it is transferred to the Digimat, which also could able to capture it quite well. Now the one what we have seen in the previous slide, that Moldflow could not able to capture the core effect well, and that gap we could see is not, we have seen it over here. And then one of the reason for that, as this beam is mainly we are testing under bending condition, where your skin effect will be more important, and we have seen that for the Moldflow it can capture the skin orientation quite well, and that is one of the reason for this particular part we have seen a very good comparison with the experimental results. As also expected over here with direct molded tensile bar, if we consider this for the simulation, it will give the over prediction of the stiffness. While if you use the quasi isotropic data, where you can expect the fibers are more random in your part, you would expect it to be much lower side. And also as mentioned, the all get open actually is coming more close to the random fiber orientation. So that's make sense, as one could expect the random fiber orientation there. But this also the results, it gives there's another clue that if many a times the designer designed the part with just a quasi isotropic material data to be a more conservative, but what that will lead to reach the required stiffness, he has to add much more material in the part. On the other hand, if he use the advanced modeling technique with the anisotropy taking the process-based fiber orientation into his design, then he could achieve the maximum advantage from that fiber orientations and then able to reduce down more weight in the part. And that's also something with the mold flow and more play with, which is the area you find critical within your part where you want to align your fiber orientation, and you can design your filling sequence and the gating location such that you get a more favorable fiber orientation in that. So that way also the anisotropic approach of the part design is also much more powerful in getting the better lightweight designs on the part. With these studies, what we have seen also, the advanced material modeling approach capture both the stiffness and strength with really a very good accuracy. The image also here on the right hand side where you could see the failed image of the real part, while here showing the high stress zone in the region, which is also the area very well matched, which also indicating the failure behavior with such modeling approach also will capture with the good accuracy with that. So with this quasi-static analysis, next we have to move to the impact studies on the part. And doing the same setup, so 4-point bending setup as shown over here. This is one of the steps where you could see the beam bending is occurring under the impact load conditions. So here we have used the impact velocity of 4 kilometers per hour, added the lump mass of 24 kg on that, and we use only the one of the beam, which is the stiffer beam, which is the top to bottom approach in that. Now, one also we have observed during the experimental studies that during the impact, due to a certain vibration of the beam, there are sometimes the loss of contact between the impactor and the beam, and due to which also we have seen there is sometimes the loss of forces. The forces are getting down. The one which also you see in the experimental result, the force curve is not really monotonically increasing. It is dropping down and the increasing, which is essentially because of the loss of contact in the part. And also you see the anisotropic results, which is actually capturing the initial stiffness aspect quite well rather. And then also it could able to capture actually all the drops in the drop in the forces because of the contact losses and all those things. Also it's captured well, and the overall behavior you could see it is falling is very well on the experimental line on that. Again, the two of the band on the upper band and the lower band, which is more looking into the molded tensile bar or the quasi iso, which is same what we have seen with the static condition, which is the same behavior what also see for the impact situation over here. Now, for this beam with this particular impact condition, we have not seen any failure happening in the part. So that aspect is not really able to capture well in the impact studies. But we would say the stiffness aspect and the strength aspect is very well we could able to represent from the studies to get a certain confidence how this coupled model can work also for the complex impact loading cases. The last example I'll show about the creep example over here. Again, as you could see here, we could use the same setup over here, the 4-point bending setup. Essentially, we have applied the load of 1830 newtons on the beam and then captured the deformation for 9 days with that, which is what you could see essentially over here, the deformations as a function of the time over here. So we could see also the primary deformation increase and then more of a secondary phase, which is more getting the asymptotic over here. And the blue line over here, which is then again the anisotropic behavior over here, which is using the elastoviscoplastic material models in that, because with this loading we have seen there is a certain plasticity in the behavior of the part. Again, we could see with the anisotropic model, the variation all across between the experimental and the simulation is within 5% accuracy, which for such long-term simulation, we could say is rather quite well captured the behavior with that. So with that, 3 studies, we could see gives a good confidence how really into short-term material behavior and the long-term material behavior, how it is captured very well with such coupled simulations, where each software, Moldflow, Digimat, and Abacus in combination will play a very, very important role in capturing the accuracy of the material behaviors in that. And such coupled simulation is surely are very, very important as mentioned for the right part design, it is very important how you can use your fibers and the fiber orientation to the more best advantage of your material behavior as well as your part behavior. So how you can use more optimally in that. And there it is very important to link the process which is coming more from the Moldflow simulations, connect with the material behavior, link with that which is coming more from the micromechanics effect from the digimat softwares, and then connect with the design which is again coming from the engineer's experience, but mainly using then the some of the structural softwares in that. But it is important to having this linkage together and then not really keep each pieces individual, and that's approach really help to give you the most optimum solutions and most optimum results with that. And with that, with the long glass fibers is surely then is the opportunity to the wider application space in the across the segment. In SABIC, we are focusing on the lot more applications. The mobility surely is the one of the key area where the light weighting is very, very important, but also there are many demanding requirements such as impact, vibrations, high temperature requirements. So there the long glass fiber really make a good fit in such applications for the metal replacement. Consumer electronics, which is want to be a more light, and then the dimensional stability. So we see also there is the good applications. And this subsequently in the various other applications where we see the long glass fiber really make a good fit there. But to make the transition into from the material to the real applications, the such advanced approach of the simulation is really one very key factors in building the confidence of the customers on that. So to conclude my presentation over here is what we have seen, that the weight saving is one of the important aspect, would say, across all the industries where their OEMs are looking for the challenging metal replacement applications with the new material forms in that. My experience is rather more into the automotive industries, and there also we see the now the new trend with the EV electric vehicles, which also demand more on the lightweighting solution so that you can increase the efficiency of the EV vehicles in that. So there is a good potential for the growth for such filled material systems into various such applications in that. But one of the key factors what we have seen is the reliability of part predictions, your material behaviors, and then giving that at the right cost efficient solution is one of the key factors customers are looking in converting the metals to the plastic designs on that. And to achieve that, there are a couple of enablers, and some of them we have touched upon today. Is one to have then the understanding of the right material behavior as the function of the fiber orientations, as shown with those shear plaque with the 04590 orientation samples, how really the material stretch strain curve change as a function of that. So it is very important to understand that. In fact, there also we have done the study at the different temperature also, so understanding the temperature effect also is important. And there OEMs are really looking for the short term and the long term material data in that. The next important is to move in building the confidence of the customers is having the advanced predictive engineering approach for such filled material systems, where where we incorporate the processes and linking that with the material behavior into the real part applications. And there each of the software which you will use for individual activities play a very important and the key role. So here, as also we have shown how the Moldflow could able to capture the behavior with the fiber orientation mainly on the skin area, and with the digimat and the abacus how could able to capture the behavior. And then finally the application design developments and then the application validation, some examples shown in this presentation, those are important to give the confidence of the customers. And this will all help really the customers the some of the benefits. Like most of the customers are looking for the metal replacement, so one of the key advantage for them, the lightweighting, the cost efficient design, because essentially with the injection molding you can have the much more robust manufacturing process with that, multiple part integration, which is the one of the key features with that. But one important features and where the advanced simulation approach is really one of the key factors there is the fast development time. Traditionally we have seen for such part development you will do a lot of then the cut the tools to check the part behavior in the reality with the real testing and all those things, and which always is then the cost intensive and also take a lot of time, so it will always then the delay the development time with that. But with the advanced simulation method, where at the first step itself you could able to capture the material behavior rather quite well, you could able to resolve this aspect actually quite quickly with that, and that really bring a lot more value to the customers in that. And surely we could look also then the smart part designs for mass production, and here also smarter design with the filled material is more use the Moldflow software to its optimum, where we can really design the gating sequences to see how we can optimally orient the fiber orientations within the part, considering how the load path is going within that part, and that way we can use the fibers to its most optimum requirement in that. So that's something is very also important, where we can connect the process design and the material aspects of it. So with that I would conclude my presentation. Thanks everyone, and if you have any questions afterwards you can feel free to reach out to me. Thank you.